On September 3rd, 2017, something very strange happened under Mount Mantap in North Korea. At a depth of nearly 450 meters below the summit, there was a nuclear device buried inside a network of tunnels carved into the rock. From the outside, there was no bomb falling from the sky, and there was no fireball over a city, nor was there the massive cloud that people usually imagine when they hear the word nuclear explosion. Everything was hidden under the mountain, and in a single moment, the device detonated. But the hundreds of meters of granite above it couldn't hide what happened. Seconds later, seismographs at vast distances began to pick up a powerful wave coming from North Korea. The Comprehensive Nuclear Test Ban Treaty Organization recorded the event and detected the seismic signal at about 6.1 on the body wave magnitude scale, meaning the Earth itself revealed the test. But the first signal wasn't the strangest thing. About 8.5 minutes later, a second, much weaker signal arrived, but its shape was different. And when scientists analyzed it, a terrifying idea emerged. The rocks under the mountain weren't just shaken, they were collapsing into the void left by the explosion. Meaning the bomb didn't just shake Mount Mantap, it changed its structure from the inside. And this is where one of the strangest remote scientific investigations began. There was no team of scientists standing on the summit, and no one could go down into the tunnel, and they didn't have a complete blueprint of a site, nor did they know exactly what the cavity left by the device looked like. Almost everything had to be understood from outside North Korea, from seismic waves and satellite imagery. And after months of analysis, a result appeared that was stranger than expected. The mountain itself had moved. Space radar data showed that parts of the Mantap surface moved horizontally outward for distances that reached, in some estimates, several meters. And then there was a subsidence in some areas. And here we need to pay attention to something important. The satellite wasn't capturing a clear crater and saying, "This is the explosion zone." What the researchers did was much more precise. They compared radar images of the site before and after the test, and monitored the very small differences in the position of the Earth's surface. And from these differences, they were able to reconstruct the direction of the movement. Parts were pushed outward at the moment of the explosion, and then areas of the surface subsided as the damaged rocks began to settle and collapse. So the image that emerged wasn't of a mountain peak that exploded and vanished. It was more like a massive block that was compressed from within, expanded for a few moments, and then parts of it settled back down. It wasn't just a rock falling from the peak. We are talking about an entire mountain mass above the explosion site that changed shape in a way that could be measured from space. And this is important because the surface movement became like an indirect window into something no one could see with their own eyes underground. One of the most important scientific models that studied the test estimated that the explosion occurred at a depth of approximately 450 meters below the peak. And according to the best result in that model, the force was around 191 kilotons of TNT equivalent. The number isn't definitive, and other studies gave different estimates, simply because no one had a measuring device inside the mountain. But the thing that is almost undisputed is that this was by far the most powerful nuclear test North Korea has ever conducted. And to understand what this means, we have to imagine the first moment underground. Around the center of the explosion, the pressure and heat were so immense that part of the granite vaporized. According to one model, a cavity about 50 meters wide was formed, and around it was a much larger area where the rocks were fractured and damaged. In the first moment, the pressure pushed the rocks away from the center, and since all this happened under a mountain, the movement transferred upwards into the sides. The surface of Mantap bulged and moved outward, and then the pressure disappeared. But what remained afterward was more dangerous: a void, fractured rocks, and above them, the weight of an entire mountain. And that's when gravity started to take over. The damaged rocks no longer had the same capacity to support the mass above them, so they started to compress and collapse inward. And this is most likely what created the second signal after 8.5 minutes. An explosion followed by a collapse, and between the two, an entire mountain changed its shape in a way that the world could see from space. But here, a more important question arises. Why was North Korea even able to create an explosion of this magnitude under a mountain without a fireball coming out of the peak? The answer lies in the location itself. The Punggye-ri site is a mountainous area full of long tunnels extending under massive rock formations. And since 2006, all 6 of North Korea's known nuclear tests have taken place in this area, underground. The idea is simple in principle. You place a device deep and use hundreds of meters of rock as a cover, and you try to trap the explosion's byproducts inside. But the 2017 test was different from all the ones before it. Previous tests left seismic signals, but this test left a much larger signal. And it moved the mountain's surface in a way that could be reconstructed using satellites. And the strangest thing is that Mount Mantap didn't return to being calm after that day. Less than 3 weeks later, monitoring devices recorded new tremors near Punggye-ri. Not new explosions. The wave patterns were closer to small natural earthquakes. And after that, more tremors appeared. Here, scientists had an unsettling question. Is this just a coincidence? Or did the explosion disrupt the balance within the rocks? The area is already capable of having natural activity. Small earthquakes happen in many parts of the world without any connection to a nuclear bomb. That's why researchers didn't just stop at the major events that were easily visible. They went back to the raw recordings and started searching for smaller signals hidden within the noise. They used the technique that compares the seismic wave pattern to previously known signals. It's almost like having a voice print and searching through a long recording for a sound similar to it. And the result changed the whole picture. A study published in 2018 examined data from 4 months before the test to about 8 months after it. And during this period, the researchers counted 88 seismic events near the area. One of them was the nuclear test itself. And one was the collapse that happened afterward, and the remaining 86 were small earthquakes. And the strange thing is that a large portion of these events were so small that they likely wouldn't have caught anyone's attention if the researchers had just relied on traditional earthquake lists. And this is where the power of the search method itself becomes apparent. Instead of waiting for a large tremor to appear on its own, they started searching through old recordings for wave patterns that resembled events they already knew about. Meaning, some of the tremors were in the data from the beginning, but no one saw them as a single story until they knew what they were supposed to be looking for. But the number isn't the most important detail. The most important thing is the timing. The researchers used the same search method before the September explosion, and they didn't find a similar series. But after the test, the activity appeared and continued for months. And the strangest thing is that some of the tremors weren't directly under the bomb site. One of the groups that scientists were able to pinpoint accurately was about 8 kilometers north of the site. And here we have to be precise. The bomb didn't create an 8-kilometer-long fault from scratch. The most likely scenario, according to researchers, is that the faults already existed, and some of them were already under natural stress. The explosion gave the system an extra push, like a heavy door standing almost at the point of balance. You didn't build the door and you didn't set its weight that way, but a small push in the right place could make it move. The study's calculations supported the idea that the stress change resulting from the test was enough to trigger part of this small chain. And the idea isn't entirely new. After underground nuclear tests at other sites around the world like Nevada and Semipalatinsk, seismic activity linked to the explosions was also observed there. But Mantap had some strange behavior. Instead of a large number of tremors appearing quickly and then everything calming down, the activity continued for a longer period at a low rate most of the time, and then it would reappear in bursts, meaning something beneath the surface was slowly rearranging itself. Rocks settling, stresses changing, and nearby faults responding to the new situation. And for years, the picture we had was limited to the first few months after the explosion. But in 2026, a new study reopened the file. This time, the researchers didn't just study a few months. They analyzed continuous recordings spanning from 2016 to 2024. And this difference is important, because when you monitor a few months after a massive event, you might see the immediate activity and assume that everything is over when the tremors start to calm down. But when you look back at years of recordings before and after the event, you can ask a more precise question. Did the region actually return to its old behavior? The researchers found hundreds of additional small seismic events around Punggye-ri, and they found that the activity rate clearly increased after the September 2017 test. Most of these tremors were very small, and that's why many of them weren't visible using traditional monitoring methods. And this is where the story became bigger than just a crater and a direct collapse. We had an event that lasted for a moment, and after that, the geological system continued to leave different signals over the years. But it's very important not to exaggerate here. This doesn't mean that every tremor that appeared for years after the test was definitely and directly caused by the bomb. The Earth is a complex system, and the region already has natural faults and stresses to begin with. But what became clear from the data is that the rate of seismic activity around the site changed noticeably after the explosion. And what makes this strange is that the explosion itself lasted for a very small fraction of a second. As for its impact within the Earth's crust, it remained observable for years. And here we return to Montap itself. After the test, a scary media phrase spread: "Tired mountain syndrome." The idea was simple. Every test adds cracks. Every crack weakens the rock, and with repeated explosions, the mountain could reach a stage where it is no longer able to contain a new test. However, the phrase "tired mountain" is not an official geological diagnosis, in the sense that scientists examined Mantap and decided it would collapse completely. The reality is more precise than that. Repeated explosions do indeed break the rocks and change their shape and stress levels. And the 2017 test caused clear deformation, internal collapse, subsidence, and landslides. But the image suggesting that the mountain has become completely hollow and could split in half at any moment is bigger than what the data actually proves. And the evidence is in the signal itself. The event that occurred 8.5 minutes later was a real collapse, and one of the studies estimated its local magnitude at about 4.1, with a movement mechanism consistent with a collapse toward the test center. I mean, the researchers weren't just relying on a satellite image alone and saying, maybe a collapse happened. They had the type of seismic wave itself, the direction of the movement, and the change in the mountain surface from above. 3 different pieces of evidence point to the same general picture. The explosion created a damaged area in an underground void, and afterward, a collapse occurred within that system. But this is not the same thing as saying the entire mountain collapsed. The summit didn't disappear, and the mountain mass didn't completely open up. And there is no evidence that Mantap became just an empty shell. And the difference between the two statements is very important, because if the rocks cracked and if parts of them collapsed, a more dangerous question arises. What happened to the radioactive materials that were supposed to remain trapped underground? This is where we arrive at the idea of containment. The reason for burying the device under hundreds of meters of rock is an attempt to prevent the explosion products from reaching the atmosphere. But every new cavity and every area of fractured rock could change the paths that gases and liquids move through underground. And after the 2017 test, wider landslides appeared than in some of the previous tests, and even signs of a change in water drainage near one of the tunnel entrances. So the question became logical. Could the cracks and water paths open a route for some radioactive materials toward the surface? International monitoring networks followed this possibility, and by April 2018, the conclusion of the Comprehensive Nuclear Test Ban Treaty Organization was clear. Its network did not detect any radioactive activity in the atmosphere that could be linked to the test or to the tremors and the collapse that occurred afterward. And here's a very interesting paradox from a scientific perspective. The monitoring network was able to hear the explosion itself, and it was able to distinguish the collapse event that followed it, and it was able to pick up small tremors that appeared later. Meaning the mountain left very clear mechanical footprints, but the thing the world was looking for in the air, radioactive byproducts that could be directly linked to the test, did not appear in a way that would allow for proving a major leak. And this doesn't mean that scientists opened up the mountain and confirmed that every atom stayed in its place. The meaning is more precise than that. No radiation release appeared on the International Monitoring Network in a way that allowed it to be linked to this test. Meaning the mountain succeeded in a fundamental part of its mission. It was able to block most of the explosion's byproducts from the outside air. But it couldn't block the movement of the Earth. It couldn't stop satellites from seeing its surface as it deformed, and it couldn't stop monitoring devices from picking up the collapse and the tremors that followed it. And here a stranger question arises. If one explosion could change the stress in the rocks around Mantap, what could happen to one of the most famous volcanoes in East Asia? Mount Pektu is located on the border between North Korea and China, and is about 126 kilometers away from Punggye. And this isn't some small, unknown volcano. About 1,000 years ago, it experienced what is known as the Millennium Eruption, one of the largest volcanic eruptions known in history. And years before the 2017 test, there were researchers already studying a strange question. Could the waves from a large nuclear explosion reach the magma system and change the pressure inside it? From a physics perspective, the idea isn't impossible. When a seismic wave passes through rocks, it compresses and stretches them for moments. And if it reaches a volcanic system containing magma and gases under pressure, it could cause a slight change in pressure. Researchers used mathematical models to estimate the magnitude of these changes with explosions of different strengths. And in some of the larger scenarios, the calculated changes in stress and pressure reached levels that researchers said were worth noting, especially if the volcanic system was already close to a state of instability. But this is where the difference between the scientific study and the sensational headline appeared. The study said, the effect is worth calculating and studying, especially if the volcano is already in a sensitive state. As for some headlines, they reduced the story to, a nuclear bomb could trigger the volcano, and this sentence is bigger than the evidence. Because a volcano doesn't have an on switch. An eruption is controlled by the composition of the magma, the size and depth of the chamber, the amount of gases, the existing pressure, and the state of the Earth's crust around it. Meaning, a seismic wave could be an additional factor within a system that is already close to instability. But there is no evidence that the 2017 test was about to trigger Pektu. And after the test, the volcano did not erupt. And that's why, instead of building the whole story on a scenario that didn't happen, there is an actual and much clearer event right in front of us. The mountain above the bomb itself changed. And here, the story shifts from possibility to evidence. Satellites saw the deformations, and seismographs recorded the explosion and the collapse, and the tremors that appeared afterward indicated that the balance under the area had changed. And all of this happened without a single scientist being inside the tunnel. And here we reach another paradox. Months after the test, North Korea announced that it would close the Punggye site. On May 24, 2018, a small group of foreign journalists stood at a distance from the tunnel entrances. And then the explosions began. The entrance to the northern tunnel, which had been used in most of the previous tests, collapsed. And then other tunnel entrances were blown up, and observation buildings and support facilities at the site were demolished. Visually, the scene was very convincing. Dust, rocks blocking the entrances, and an entire nuclear site closing down in front of foreign cameras. But there was a problem. The people standing there watching were journalists, not international inspectors, not nuclear weapons experts going inside the network, and not geologists with equipment to know how far the damage extended underground. The world was able to confirm that the entrances were blown up, but it couldn't confirm that the deep tunnel network had become completely unusable. And that difference turned out to be important 4 years later. In 2022, satellite imagery began to show new activity at Punggye, roads being repaired, buildings reappearing, and construction work near one of the tunnels. And in June of that same year, the International Atomic Energy Agency said it saw signs of one of the entrances being reopened, and linked this to the possibility of preparing for a new test. And after that, the assessment became clearer. Tunnel number 3 was reopened, and the site remained in a condition that could support a new nuclear test if the decision were made. And here, the 2018 scene changes completely for us. At the time, the world saw explosions, dust, and entrances collapsing, and it was very easy to imagine that the site had become a thing of the past. But satellite images years later said something different. Destroying the entrance is not necessarily the same thing as destroying the entire deep tunnel network. And this is exactly why it's important to have independent inspectors and experts when you want to know if a complex facility has truly become unusable. I mean, after all the explosions that the journalists saw, Punggye didn't disappear. And here we reach the biggest irony in the story. The 2017 test was so powerful that it deformed Mount Mantap and caused an underground collapse, followed by tremors that lasted for a long time. After that, North Korea blew up the site's entrances and announced its closure. Yet, years later, the site returned to a state that could allow it to be used again. And in subsequent official assessments, Punggye continued to be described as a site prepared to support a new test if the political decision was made. And here, there is a distinction that must remain clear. Readiness does not mean that a test has taken place. The presence of activity at the site, open roads, or a prepared entrance does not equate to a nuclear explosion. And that's why scientists and agencies always go back to the evidence that is hard to interpret in more than one way. The seismic signal characteristic of an explosion. But despite all this preparation, the 7th test didn't happen. At least, there has been no new nuclear test confirmed after September 3, 2017. The Comprehensive Nuclear Test Ban Treaty Organization still considers this the last confirmed nuclear explosion captured by the International Monitoring System. And this makes it a very important benchmark for any new news that might come out about Punggye in the future. Satellite images might say there is digging, roads, buildings, or activity. And political statements might say the site is ready. But the moment of the test itself leaves a different kind of evidence. Seismographs don't need to see the tunnel, and they don't need North Korea to announce what they've done. If a large underground explosion occurs, the waves will travel through the rock and reach the monitoring networks. And here we return to the very first moment of the story. A nuclear device buried under hundreds of meters of rock. The whole concept of the site is based on hiding the explosion inside the mountain. And to a large extent, they managed to hide many things. No one saw the device, and no one saw the moment of the explosion from the inside. And even the true power of the bomb, scientists had to estimate it using various models. But there is one thing they couldn't hide. The Earth itself. When the bomb exploded, the waves traveled through the Earth's crust and reached distant stations. And when the rocks collapsed after 8.5 minutes, the Earth gave a second signal. And when the surface of Mantap moved and sank, satellites detected the change. And when the pressure in the rocks changed and aftershocks appeared, measuring instruments continued to pick them up. And that's why when we hear that Mount Mantap collapsed, the more accurate picture isn't that the mountain disappeared or split down the middle. What happened is more complex than that. A massive block of rock was subjected to very sudden pressure. Part of it shattered, and part of it moved, and part of it collapsed toward the blast zone. And then the whole system began to redistribute the pressure within itself. And scientists were able to reconstruct a large part of this story from entirely outside the country. And the strangest thing is that the site that produced this event still exists. And the world is still monitoring it to this day. Because if the 7th test happens one day, North Korea might seal the tunnel, hide the device, and prevent anyone from getting close. But there is one thing that is very difficult to prevent. When you shake a mountain with a nuclear bomb, the planet itself becomes a witness against you. If you think that underground nuclear tests are more dangerous than people imagine, or conversely, you believe that the rocks are capable of containing them safely, write your opinion in the comments. And if you like this kind of true scientific story, subscribe to the channel.